This lesson is edges, faces, and vertices using the 3D nets. In Appendix B in the teacher's manual, you'll see that there are several 3D nets. And on a 3D net, basically you have a two-dimensional representation of a three-dimensional shape. These can be cut out along the solid line on the outside, and then these gray marks on the paper, these are the tabs that will slide in when you fold it. So it's very challenging for a lot of students to be able to look at a 3D net and be able to determine how the shape goes together. Generally, though, they can tell what actual type of shape it is. In this case, we have the cube laid out here, and the cube has 6 sides, and every single side is made up of a square, so every side is the same shape with the same dimensions. On here you can see that every angle is labeled with a lowercase letter, and each face is labeled with a bold number. So the purpose of today's lesson is to teach students how to determine the number of faces, edges, and vertices on a 3D net. We're going to use board number 35, and we're going to start off with Euler's formula. Euler's formula basically shows the relationship between vertices, faces, and edges. So on any given three-dimensional shape, the number of vertices plus the number of faces minus the edges equals 2. So I'm going to work with that formula on this three-dimensional net, and I'll start off with the easiest one, the number of faces. Count them 1, 2, 3, 4, 5, 6, because they're labeled. So in this case, I will replace the faces with the number 6. And the 2 is constant. I believe the next easiest variable to find on this is the edges. So what we'll do is we'll have students calculate the number of edges or determine them by trying to visualize. Now you can actually cut this out, put it together, and it's much easier for students to be able to count the edges. So if they have a problem or a difficulty in determining how many edges there are from a two-dimensional shape, you can go ahead and cut them out, and it becomes much easier. So here we can see that 2 and 3 meet right there, that's one edge. 3 and 1 meet, that's 2 edges. 3 and 4 meet, that's 3 edges. And 3 and 5 meet, that's 4 edges. Now the tricky part is how do the other ones come together? Well, when this folds underneath, 4 and 1 actually meet along this edge, and 2 and 1 meet along this edge. So we have the 4 original plus 5 and 6. So plus these 2, that's a total of 6. Then on the same here, these 2 edges meet, and these 2 edges meet, so that's 7 and 8. And then this edge meets, that's 9. And then this edge meets up here, that's 10. And then in addition, you have this and this one meet when it folds under, so that's 12. So we actually have 12 edges. So given that, we can easily determine the number of vertices because that is the missing variable. So we do B equals, we take this onto the other side by adding 12 to both sides. So we have B equals 2 plus 12, and then we subtract 6 from both sides, minus 6. So the number of vertices is 14 minus 6, which equals 8. So again, I believe it is much easier for students to cut these out, put them together, and they can see the relationship, but you can also use Euler's formula to be able to calculate and look at the two-dimensional representation.